Right now, hold a glass in your hand. Not metaphorically, really imagine the weight of it, the chill on your fingertips, the way it catches a stripe of window light and throws it back at you like a clean, hard promise. You rotate it. It feels certain, rigid, final. And then a single thought slips in like a crack you didn't see coming. If this thing is made of atoms that never stop moving, what does solid even mean? I'm Rowan K. Mercer. And tonight, we're going to audit something so ordinary you've stopped seeing it, until it starts to look like a paradox. Because here's the human-sized mystery. If you set that glass down and walk away for 1,000,000 years, will it still be the same shape when you come back? I want you to feel the weight of that question. Not as trivia. As a test of what you trust. Because we all live on the assumption that some things are stable. That a table is a table. That a window stays a window. That matter can be counted on to hold still while we build lives around it. And yet the physics under your palm is restless. Everything is vibrating. Everything is negotiating with heat and time. The solid world might be less like a fortress, and more like a slow-motion argument. Now, before we touch the science, we need to visit a story that spreads like a rumor through museums, classrooms, and casual conversations. You may have heard it. In medieval cathedrals, old windows are thicker at the bottom. And the myth says, aha, glass flows. Over centuries it slumps downward like an impossibly slow liquid. It's delivered with that delicious tone of secret knowledge, the kind that makes you feel like you've peeked behind reality's curtain. Tonight we won't swat that myth away immediately. We'll treat it like a clue at a crime scene. Because even if the myth is wrong, the question underneath it is still alive. If glass doesn't flow in any way you can see, is it still, in principle, a liquid caught in the act of taking its time? Here are the rules of our audit, simple, but strict. We're going to separate 3 things that usually get tangled together. 1. What glass actually is on the inside. 2. What solid even means in physics. And 3. What time does to disorder, especially when time is long enough to embarrass human intuition. So let's step into the lab mindset. Imagine the world as a set of tests you can do with your hands. You press a thumb into a sponge, it yields, then springs back. You press a thumb into honey, it yields, and it keeps yielding. Same push. 2 totally different stories. That difference, spring back versus keep flowing, is a doorway into the meaning of solid and liquid. In everyday language, a solid is something you can pick up, a liquid is something that takes the shape of its container. That's useful for cooking. It's not precise enough for physics. Physics asks, if I apply a shear stress, if I try to slide the top of the material relative to the bottom, what happens over time? Shear is a fancy word for a simple action. Picture a deck of cards. Put your hand on top and push sideways. The cards slip. That sliding is shear. A solid, in the strict physical sense, resists that sliding. A liquid can't sustain it. Under a constant shear, it will keep deforming. And here's the first twist that makes this whole topic feel like it's alive. In physics, the answer depends on timescale and temperature. Timescale is the part we forget because our bodies come with a default setting. We live in seconds, minutes, years. But matter doesn't care what we call a long time. Matter has no respect for your calendar. If you push a material for 1 second and it springs back, you call it elastic. If you push it for an hour and it slowly creeps, you call it viscous. And some materials are both, depending on how patient you are. Let's make that tactile. Imagine you take a rubber band and pull it. It snaps back quickly. Now imagine you take a thick blob of pitch, the black tar used in roofing, and you nudge it. It looks like a solid. It can shatter if you hit it. But over months or years it creeps. There's a famous experiment where pitch drips through a funnel, 1 drop every decade or so. It behaves like a solid when you're impatient, and like a liquid when you're immortal. So already, the categories blur. Not because language is sloppy, but because the world is. Solid and liquid aren't always different substances. Sometimes they're different answers to the same question asked at different speeds. So where does glass sit? Here's where we take that everyday object and start to see its inner architecture. If you could shrink down past the thickness of hair, past the width of bacteria, down to the scale where atoms are the size of planets, and walk through glass like a city, you would not find neat streets. You would not find repeating blocks. You would not find the crystalline order of salt or diamond, where atoms lock into a lattice like a perfectly tiled floor. In a crystal, if you know where one atom is, you can predict where a million others are. Order repeats. That repetition is like a rhythm you can dance to. Glass is different. Glass is amorphous, meaning, without a long-range shape. It has structure, but not the kind that repeats like wallpaper. It's more like a snapshot of a liquid, taken mid-swirling, then frozen before it can settle into a pattern. A metaphor that actually does work here: imagine a crowd leaving a stadium. In a calm exit, people self-organize into lanes, flowing toward doors. That's like crystallization. Particles find an ordered, low-energy arrangement. Now imagine the doors suddenly narrow, the lights cut out, and the temperature drops. People stop moving where they are. The crowd becomes rigid, not because it's organized, but because it's jammed. You can't easily shove through it. That's one way to feel what glass is like. Now you might ask, if glass is like a frozen liquid, doesn't that mean it must have a melting point like a crystalline solid? Here's the second twist. Glass doesn't have a sharp melting point the way crystals do. When a crystal melts, there's a specific temperature where its order collapses. It's dramatic. It's a phase transition with a clean line in the sand, solid here, liquid there. But glass goes through what we call the glass transition, a range where it softens from rigid to rubbery to flowing as you heat it. It's less like a switch and more like dawn. The world doesn't go from night to day in one instant, it gradients. And that gradient, this gradual softening, whispers something important. Glass is not a substance in equilibrium the way a crystal is. It's a material that fell out of equilibrium. Hold that thought, because it's the key that opens the whole mystery. But first, we return to those cathedral windows. You've probably seen the pictures. Old panes, thicker at the bottom, thinner at the top. It's tempting to imagine gravity pulling on them like taffy over centuries. It's such a satisfying story because it makes time feel tangible. It turns architecture into a clock. The problem is, it's not what happened. Most of those windows were made with historical manufacturing methods, crown glass and cylinder glass, that produced panes with uneven thickness. When builders installed them, they often put the thicker edge at the bottom for stability, because why wouldn't you? If you've got a slightly lopsided pane, you mount the heavy side down. That's not a million-year physics experiment. That's a practical decision by a craftsperson. So the myth fails as evidence. But, and this is crucial, it fails in a way that makes the deeper question more interesting, not less. Because if the windows aren't sagging visibly, then the persistence of their shape becomes even more mysterious. What kind of solid is so disordered inside, yet so stubborn outside? Now we slow down. Because we've reached the border where definitions start to fail. Glass is rigid like a solid, but disordered like a liquid. It doesn't fit comfortably in the tidy drawers our minds love. So we need a new concept, and I want to introduce it gently, like handing you a tool you'll use for the rest of your life. The concept is kinetic arrest. Kinetic refers to motion. Arrest means stopped. But not stop the way a photograph stops a runner, by ending the story. Stop the way a crowded highway stops traffic, by making motion so slow and constrained that, for all practical purposes, it might as well be frozen. In a liquid, atoms rearrange constantly. They have enough thermal energy, enough microscopic jiggling power, to slip past each other, to explore new configurations, to find lower energy arrangements. In a crystal, atoms also move, but they vibrate around fixed positions in a repeating lattice. The lattice is a deep groove in the universe's record, and the atoms rattle inside it. In a glass, as you cool the liquid, the rearrangements become harder and harder. The viscosity skyrockets, meaning the resistance to flow becomes enormous. The atoms want to find an ordered state, often a crystal, but they don't get the chance. The cooling outruns their ability to reorganize. Motion doesn't vanish. It slows until rearrangement times become longer than your patience, longer than your lifetime, longer than civilizations. So the system falls out of equilibrium. That phrase matters. Equilibrium is not a moral achievement. It's a condition, the idea that a system has had enough time to settle into the most probable state given its energy and constraints. In equilibrium, properties don't drift with time. They're stable because the system has finished negotiating. Glass is what happens when the negotiation gets interrupted. It's like stopping a movie halfway through and calling that pause frame the final story. The characters are mid-gesture. The plot is unresolved. The scene is stable only because you've taken your finger off the play button. But of course, the universe doesn't have a pause button. So how can glass be stable at all? Here's where we need the energy landscape metaphor. And I don't mean metaphor as a poetic decoration. I mean metaphor as a way to compress a brutal amount of mathematics into a picture your brain can carry. Imagine every possible arrangement of the atoms in a piece of glass. Not just a few possibilities, an absurd number. Numbers with more zeros than there are atoms in the observable universe. Each arrangement has an energy. Some are comfortable and low, some are strained and high. Now imagine plotting that energy as a landscape: mountains, valleys, passes, cliffs. Each point on the map is one atomic arrangement. Low valleys represent stable configurations. High ridges represent unstable ones. A liquid is like a traveler with enough energy to hop between valleys. It wanders. It explores. It doesn't get stuck for long. A crystal is like finding the deepest, broadest valley and setting up a permanent city there. It's ordered because it's energetically efficient. A glass is like a traveler caught in a valley that isn't the deepest one, just one the traveler happened to be in when the temperature dropped and the jumping became impossible. The traveler is trapped. Not finished. Not at the best destination. Just stuck. And stuck is the heart of the glass mystery, because it introduces a new kind of stability by slowness. Now, here comes a question that should make you sit up a little straighter. If the traveler is stuck but not finished, then given enough time, shouldn't it eventually escape? Shouldn't glass eventually relax? Shouldn't it flow? That's the question people are really asking when they say, "Is glass a liquid?" They're asking, is rigidity permanent, or is it just the illusion created by our short lives? So let's stress test this reality model with 3 thought experiments. And I want you to do them with me, as if we're standing at a bench with a notebook, not watching a lecture. Thought experiment 1. You leave the glass for an impossibly long time. 1,000,000 years. 10 million. 100 million. On those timescales, continents rearrange. Species blink in and out. So what about your glass? Does it slump? The honest scientific answer is nuanced. At room temperature, ordinary soda-lime glass has a viscosity so high that any flow is negligible on human and even historical timescales. That's why your windows don't puddle. That's why your drinking glass keeps its shape. The timescale for significant flow at room temperature is so vast that forever becomes a practical description. But in principle, because the material is not in true equilibrium, there can be extraordinarily slow relaxation, so small you'll never see it, yet real enough to measure in sensitive experiments. That takes us to thought experiment 2. You heat the glass slightly. Not to melting. Just warm it. If glass were a normal crystal, you'd expect a crisp transition, solid until a point, then suddenly liquid. But glass softens gradually. Why? Because you're not breaking a repeating lattice. You're giving the trapped traveler a little more energy to climb the ridges around its valley. Different regions in the material have different local constraints, different microscopic cages. So the unlocking happens over a range. Some parts start to rearrange while others remain jammed. The whole material becomes viscoelastic, partly springy, partly flowy. And yes, viscoelastic sounds like jargon. But you already know it. You've felt it in chewing gum, in silly putty, in warm polymers, in the way some things bounce and ooze depending on how you treat them. Viscous is the tendency to flow and dissipate energy, like honey. Elastic is the tendency to store energy and spring back, like a trampoline. Viscoelastic materials do both. They remember your push, and they forget it. Thought experiment 3. You tap the glass. Not hard enough to break it. Just a gentle mechanical nudge. Then you do it again tomorrow, and next week, and next month. Can the glass age? Can it change its properties just by existing under small perturbations? This is where the story gets quietly eerie. Because glass does age. Not like wood rotting or metal rusting. Glass ages internally. Over time, even at constant temperature, the structure can relax toward lower energy configurations. This changes measurable properties. Density can increase slightly, enthalpy can relax, mechanical response can shift. The material can become subtly stiffer or more brittle, depending on history. Time becomes measurable inside the matter. Physicists even use a concept called fictive temperature. It's not a fake temperature in a dismissive sense. It's a way of saying, the structure of the glass corresponds to the state the liquid would have had at some temperature when it fell out of equilibrium. The glass carries a memory of its cooling process, like a fossil carries a memory of an ancient sea. That's not poetry. That's experiment. If you cool glass quickly, you trap a higher energy structure. If you anneal it, hold it near the glass transition and let it relax, you allow it to settle into a lower energy state. Two pieces of glass with the same chemical composition can behave differently because their histories differ. So now we're staring at something profound. Glass is a solid that remembers. A rigid object with a biography. And if you're thinking, okay, so why is this such a famous unsolved problem? Why do scientists still argue about glass? Good. That curiosity is exactly where the frontier begins. Because the glass transition is notoriously hard, not because it's mystical, but because it sits in a blind spot between two great frameworks. Thermodynamics is the science of equilibrium, of what states are possible and how energy and entropy shape them. It's powerful, clean, and often indifferent to time. Dynamics is the science of how systems move through states, how fast they rearrange, what pathways they take, how motion slows. Glass is where thermodynamics and dynamics collide, and refuse to give a simple answer. When a liquid crystallizes, there's a clear symmetry breaking. The system goes from disordered to ordered. It's like a crowd suddenly organizing into a marching formation. That gives you a crisp signal to track. But when a liquid becomes glassy, there's no obvious new order parameter, no simple symmetry breaking you can point to and say, that's the moment the universe changed its mind. Instead, you see a dramatic slowdown in dynamics. The viscosity rises by many orders of magnitude over a relatively small temperature range. It's as if the internal clock of the material is being dialed down, tick by tick, until rearrangements become astronomically rare. So what causes that slowdown? There are competing theoretical ideas, and I want to present them the way you'd hear them if you were standing in a hallway at a conference, because this is living science, not settled scripture. One cluster of ideas emphasizes dynamical slowdown. As temperature decreases, motion becomes increasingly cooperative. Instead of single atoms slipping past neighbors, groups must rearrange together. Picture trying to change seats in a packed theater. One person can't move unless several people coordinate. As the theater fills, rearrangements require larger and larger coordinated groups. That cooperation makes motion rarer and slower. Another family of theories, like random first-order transition ideas, imagines the energy landscape becoming a maze of metastable states, many valleys separated by increasingly high ridges. The system isn't heading smoothly toward one destination, it's confronted with a combinatorial explosion of traps. Mode coupling theory offers a mathematical description that captures aspects of the slowdown, especially at higher temperatures, but it's not the final word near the deepest glassy regime. The key message isn't, we know nothing. The key message is more subtle. The phenomenon is real, measurable, and ubiquitous, yet our cleanest, simplest universal explanation still feels just out of reach. And that should not make you cynical. It should make you feel the thrill of standing at a seam in human knowledge where the fabric is still being stitched. Now let's bring this back down from the mountain to the kitchen table, because that's where the all becomes personal. We began with a glass in your hand and a question about solidity. We've learned that solid is not an eternal label stamped on matter. It's a statement about how matter responds on a given timescale, at a given temperature, under a given stress. This is the philosophical turn, and it's not philosophy as decoration. It's philosophy as consequence. Glass teaches that categories like solid and liquid can be context-dependent. Not subjective, Physics is still physics, but dependent on observation conditions. If you judge with human senses and human lifetimes, glass is solid. If you judge with a theoretical eye that imagines infinite time, the boundary gets strange. And then there's something even more unsettling. Disorder can be a legitimate kind of structure. We tend to equate stability with order. Neatness feels strong. Symmetry feels permanent. But glass is rigid while being disordered. Rigidity can come from trapped complexity, from being jammed in a configuration space too tangled to unwind easily. The universe has more ways to make something stop than just arranging it perfectly. That idea spills far beyond windows. Metallic glasses, metals cooled so fast they don't crystallize, can be extraordinarily strong and elastic. Polymers, long molecular chains, can behave glassy, rubbery, or viscous depending on temperature and timescale. Granular materials like sand can jam. A flowing avalanche becomes a stable pile without any crystalline order. Traffic can freeze into a jam without anyone intending it. In biology, the interior of a cell is crowded and complex. Molecular motion can become glass-like, with dynamics that slow and constrain life's processes. In all these systems, the common theme is not solidness. It's arrested motion. It's the way complexity can lock a system into rigidity without giving it the neatness of a crystal. So now, come back with me to the exact moment we started. The same kitchen. The same light. The same glass. You turn it again. It still looks like certainty. But now you see the deeper truth hiding in plain sight. This object is not a frozen river that used to be a liquid and is now finished. It's more unsettling than that. It's a material still negotiating with time, only so slowly that we mistake that negotiation for permanence. And if you let that sink in, it changes something small but permanent in the way you look at the world. Because the next time you see something, still, a pane of glass, a plastic casing, a road surface, even a crowded room that feels locked into place, you'll know to ask a more precise question then. Is it solid? You'll ask, still on what timescale? Here's the synthesis, clean and honest. Glass is an amorphous solid, structurally disordered like a liquid, mechanically rigid like a solid, because its internal rearrangements have become unimaginably slow. The cathedral window myth is not evidence of flow, it's a story built on uneven manufacturing and installation. Yet glass does evolve, through aging and relaxation, so subtly that only careful measurement reveals the motion hiding under the stillness. The deepest mystery is not whether glass is, really, a liquid, it's why dynamics slows so dramatically without a simple, universal signature of new order. Now a thought experiment to carry into your own life. Imagine two identical glasses. Same shape. Same composition. One was cooled quickly in a factory rush. The other was annealed patiently, given time to settle. They look identical. But inside, they are not the same. One holds a slightly different memory of heat and haste. If you could feel that difference with your fingertips, would you live differently, more attentive to the hidden histories inside the same objects, and inside yourself? And the next great question, the door we haven't opened yet, is this: if the boundary between solid and liquid can be a matter of timescale, what does that say about other boundaries we take for granted, like the boundary between past and present, or between memory and reality? If you want to keep going, click the video on the end screen, because it picks up this thread and pulls it into a place that will genuinely rearrange how you see the world. And if you want more audits like this, subscribe, not for news, not for trivia, but for the habit of looking at ordinary reality until it confesses what it really is. One question for you, and I want a simple, honest answer in the comments. When you hear glass flows, do you feel wonder or discomfort? Why?